Coordination is a process that you'll see again and again when studying the nervous system. A prime example of this is in movement. Animals use muscles to perform movements, but muscle can only apply contractile or pulling forces. They can't generate pushing forces. This means that to be able to both flex and extend your legs requires two antagonistic muscles that work against each other. One muscle pulls the leg to flex it, the other pulls to extend it. This principle is used throughout the musculo-skeletal system. If you want to walk down the hall, then you must be able to coordinate the contraction of the antagonistic muscles in your legs so they don't fight each other and so they provide the right timing to produce a walking motion. The contraction of the two muscles must be out of phase with each other. Movement of muscle is controlled by central pattern generators located in the spinal column. The fact that central pattern generators can have their phases reset by injected current means that if independent oscillators are coupled by synapses, they can mutually entrain each other. This tutorial will show you how to coordinate bursting neurons so you can build organisms that exhibit coordinated movements. Let's begin by creating a new project. A copy of this tutorial is located at Program Files, AnimatLab, Tutorials, Neural Networks. Choose where you want to create this project and then call it Coordination. Once you have a project, create a new organism and open its behavioral editor. Then add two spiking neurons to the diagram. We're going to configure these neurons to be endogenous bursters. They'll be the central pattern generators that will be coordinating. Set the maximum calcium conductance to 18 microsiemens, the activation slope to 0.12, the activation time constant to 8 milliseconds, and the inactivation time constant to 2000 milliseconds. Do this for each neuron. Now create a line chart so we can see the membrane voltages of our two neurons. Set the end time to 1.5 seconds. Collect data interval to 0.2 milliseconds. Points to keep to 15,000. And update interval to 250 milliseconds. Now run the simulation. You can see that we get two bursting neurons that are behaving identically. Now let's couple the two neurons together using weak reciprocal inhibition. Draw a synapse from neuron 1 to 2 and select the hyperpolarizing IPSP synapse type. Change the conductance to 0.1 microsiemens, facilitation to 1, and the facilitation decay to 1 millisecond. Then add another hyperpolarizing IPSP synapse from neuron 2 to 1. When we ran the simulation last time, the two neurons behaved identically. This is unrealistic because in nature all neurons have a certain amount of noise. Let's fix this by adding 0.2 millivolts of noise to each of the neurons. Now run the simulation. This time we get something different. Initially they burst in phase, but the reciprocal inhibition rapidly forces them to oscillate in antiphase. You can see this happen around 0.5 seconds when neuron 2 stops the burst from neuron 1 and delays it till after its burst is over. This demonstrates how to get two central pattern generators that burst out of phase with each other. But sometimes central pattern generators need to remain in phase as well. An example of this is the difference between walking and hopping. During walking, the two legs swing out of phase, but in hopping, they act in phase. To do this, begin by deleting the two synapses that we just added. Then let's change the bursting properties of neuron 1 so it's no longer the same as neuron 2. This will make them become slightly out of phase as they continue to burst. Set the inactivation time constant to 1500 milliseconds. Rerun the simulation, and this time you can see that the two neurons are slightly out of phase. Now go back and draw synapse from neuron 1 to 2. Select the nicotinic acetylcholine synapse and clone it. Name it weak EPSB. Set its conductance to 0.1 microsiemens, decay to 10 milliseconds, facilitation decay to 1 millisecond, and facilitation to 1. Then add another weak EPSB synapse from neuron 2 to 1. Run the simulation again. This time the neurons that were slightly out of phase burst together. You can also produce coordination using the more abstract firing rate neural models. Close the current chart and then add two pacemaker neurons to your diagram. Set the V sub SSM parameter to be 0. This will allow the neuron to burst without any external stimulus. Add 0.4 millivolts of noise. Set the value of B sub TL to 2 seconds, and set the gain to be 10. Do this for both neurons. Create a new line chart and add items to view the firing frequency and membrane voltage for both neurons. Set the end time to be 20 seconds and points to keep as 15,000. Run the simulation. We can see that the two neurons are bursting in phase. In fact, without the noise, they'd be operating identically. Now let's add some reciprocal inhibition between these two neurons. Add inhibitory synapses that are negative 15 nanoamps strong between the two neurons. This time, when we run the simulation, after the very first burst, the reciprocal inhibition drives the two pacemakers apart. This way, they're bursting out of phase. This tutorial has demonstrated how to coordinate the action of central pattern generators.